my talk today will be very introductory. I will introduce every concept that you may be curious about on quantum walks. So, as I promised, I'll give an overview of the most important quantum walk models. I will speak a little bit about how we can simulate it classically to study the quantum walks and to learn more about them, and how we can implement them on real quantum devices, like IBM devices, for example. And I will give some algorithmic applications. What can we do with quantum walks in terms of algorithms? So let's start with the quantum walk models. So the general idea is that, let me keep track of time, otherwise okay. Yeah. So the general idea is that the quantum walk, as the name suggests, is the quantum version of the classical random walk. So in a classical random walk, we have a set of states that we can represent by vertices in a graph, and we have transition rules that we can represent by the edges or the possibly directed edges on this graph. And we have some probability of making each transition, which we can organize in a matrix, and this matrix must satisfy some property. It must be a stochastic matrix because we want to keep the vector as a probability vector, of course. So we set the initial position of this walker, and then we toss a coin or something analogous to that, and we repeat that process several times, and from that we can obtain several properties and we can develop algorithms. And there are many algorithms that are developed under this framework. Just as an example, I mentioned here the Schoening algorithm for set problem, satisfiability problem. It's based on random walks. So it's based on this very simple process of tossing a coin and then changing the state accordingly. And mathematical representation for that can be given by this matrix vector multiplication. So we have an initial probability distribution represented as let's say a column vector, and then you multiply it by a stochastic matrix, and then you have the next step, the next probability distribution. And this is the classical setting. And for a quantum walk, we must replace this by this walker by a quantum walker, by a quantum particle. So we must obey the postulates of quantum mechanics. So we can also use this quantum framework of quantum walks to develop interesting algorithms. So just as I mentioned Schoening's algorithm in the classical setup, I can mention, for example, the quantum algorithm for element distinctness in the quantum setup. I will talk more about that later. So how can we convert this classical setup into a quantum walk? So let's first give a try with a very straightforward approach. Let's say that we have a quantum walker, so to obey the postulates of quantum mechanics, the state of this walker must be a vector on a Hilbert space. So let's say that the position of the walker is given by this unit vector. This unit vector can be in a linear combination of the vertices of the graph. Those coefficients, A, B, C, and so on, they are complex numbers in general, and they must satisfy this constraint that the modulus square of the coefficients must be, when we sum all of them, must be equal to 1. And that's because the modulus square of this coefficient is related to a probability. It's the probability of measuring the walker, and then we will observe that the walker is in a certain state of the graph. So this is the first postulate of quantum mechanics. There is another postulate of quantum mechanics that says that the evolution of the system is given by a unitary operator. So instead of a stochastic matrix, that we had in the classical setup. Now we must have a unitary matrix, this U matrix. Okay? So basically that's it. So we write a unitary matrix instead of stochastic matrix, and so we could have a quantum walker. But then what's the problem? The problem is that it could be boring if we are naive when building this unitary operator, because in general it can lead to very straightforward dynamics, nothing very interesting. So we must be very careful when building this unitary matrix. So there are several ways of consistently defining a quantum walk with very interesting dynamics. We can classify those models into discrete time and continuous time. The space is always discrete, it's always a graph, but the time can be discrete or continuous. The discrete time quantum walk can be of different flavors as well, can be the coin, the Zeged model, the Zeged. I will talk a little bit about each of them. So let's start by the coined quantum walk. Quantum walk was developed in 1993 by Haranov, Davidovich, and Zaguri, and that's the idea. The idea is adding an extra space, an extra quantum system. So we have one quantum system to represent the position of the walker, but we need some additional system or an additional degree of freedom to represent the coin. So let's say that we have this graph here, this cycle, and then the walker can move clockwise or counterclockwise. So we have two different directions that can move. So we need an extra state that is two-dimensional, that will be enough. So this extra state can be represented by this coin state. It's a linear combination of two vectors, let's say clockwise, counterclockwise, 0, 1, doesn't matter. And then at the end we have the position of the walker and the coin state. And the system as a whole is described now as tensor products. It's also because of the postulates of the quantum mechanics. So when we have a composed system, the state of the system as a whole is the tensor product of the subsystems. So the generic state is this psi vector, and those psi inside the summation are the complex coefficients, and they must satisfy that constraint. The sum of the modulus square must be equal to 1 to keep everything consistent at every time step. So at the end we have an evolution given by a unitary operator, of course, but this is not any kind of unitary operator. It's very specific, very special. It's a unitary operator represented by the composition of a coin operator and a shift operator. So this C matrix is a coin operator, so it will act only on the coin subspace, that two-dimensional space in our example. So if you represent it by a matrix, it should be a 2 by 2 matrix, like that. And then we have this S operator, which is the shift operator, and then it actually moves the walker. So it's responsible for moving the walker. So in our example, we have a shift operator that goes clockwise if the coin is 0, and counterclockwise if the coin is 1, for example. But of course, we can generalize that for any kind of graph. The only restriction, the only constraint is that the shift operator must, of course, respect the neighborhood of the vertices. It cannot jump and stay. That's not connected by an edge. So that's it.
Sorry.
Yeah.
Why can't you map this model on another, so to say, trivial quantum walk where you have twice the states on the circle and no coin? this should be possible, right?
You mean changing this?
This to another, then you have 7, 8 states, you can have a 16 and redefine your unitary in such a way that it maps exactly.
Yes, we can do that.
Okay.
Yes, we can do that. And then you have to choose a coin state that respects the degree of the graph. If each vertex has a larger degree, then it should have a larger dimension as well, but we can do that.
No, but what I'm saying is that to just remove the coin state and
to remove the
a graph which is twice as large,
Okay.
and redefine your unitaries so that you map exactly your model with coin and model.
Okay, so
It should be possible.
it should be possible because then some states would be doing the role of a coin somehow. Yeah.
But you said before that without coin is somehow trivial because of this logo theorem. So
Yeah,
this pose a problem.
Yeah, no, what I mentioned before is that if we do that carelessly, then it will lead to trivial dynamics. But we have a discrete time quantum walks that doesn't have coins. You have coinless models. But then they have to do some tricks to reach interesting dynamics. Yeah, but it's possible. And then if we measure the position of the walker after some steps, we find some beautiful patterns like that, very different from the classical ones that we are used to see. And we can notice like a inference pattern that's very typical of quantum systems, of quantum processes. So that was the coined quantum walk. As I said, we have different models, and a very interesting model is Zagidi's quantum walks. It is a coinless model of quantum walk. The origin of this model can be traced back to the algorithm for element distinctness from 2003, and it was later generalized by Mario Zagidi to present a quantum walk based on a classical Markov chain. So it's a very general process. There is a recipe. If you have a classical Markov chain, you can define a quantum walk following this recipe. So we must start by a bipartite graph. Of course, if the original graph is not bipartite, we can still do it, but we have to pay the price of duplicating the vertices to make it bipartite. Okay. So let's assume that we have already a bipartite graph, and then we need two matrices, one to map, one with all the probabilities mapping the vertices on set X to the vertices on set Y, and vice versa. We need another matrix to map backwards from Y to X. And then, for each pair of vertices, or for each edge, let's say, we have a state like this. We need a vector space where the basis of this vector space is this set of edges. So the vector space is generated by the edges of the bipartite graph. Okay. And then we define unit vectors by associating the probabilities of transitions from one set to the other, and then we use those probabilities to define those unitary vectors, right? Those phi and psi. So we can understand that as one unit vector for each edge of the graph. Okay. Okay. So once we have those unit vectors, we can define those projectors here. Those projectors R0 and R1, and that's it. We can use those projectors to walk on the graph, and Zagidi showed in this paper how it consistently defines a quantum walk. And that's basically the idea that was used for the element distinctness algorithm. I will talk more about that algorithm later. And we still have at least one more interesting model of quantum walk, which is the staggered quantum walk. This is much more recent. It's from 2016, based, of course, on some previous ideas of doing this kind of coinless quantum walk. So before I talk properly about staggered quantum walk, I need to introduce some concepts, some definitions. The first definition is the tessellation. So we say that a tessellation is a partition of the vertices of the graph into cliques. Right? So we need to partition the graph into cliques. We say that one edge belongs to a tessellation if both endpoints are in the same clique of that partition. So, for example, we have this green tessellation here. This green tessellation. We can say that this edge, I don't know if you see my mouse pointer here. Mm-hmm. So this edge here belongs to the green tessellation. But this other edge here does not belong to the tessellation. So of course, by definition, with one single tessellation, we cover all the vertices, of course, but not all the edges. But then we can have more tessellations. Now I have one green tessellation and one red tessellation for the same graph. And then now this edge that was not covered by the green tessellation, it is covered by the red tessellation. And we can go on with this process until we have enough tessellations to cover not only the vertices, but also the edges, all the edges. And then we say that this is a tessellation cover for the graph. And we need a tessellation cover to define this quantum walk. That's the initial idea. And this tessellation problem for graphs is very interesting. It's a very rich problem. And we can study that problem by its own. Even if you're not interested in quantum walks, you can perhaps be interested in the tessellation problem because it's very nice. The initial motivation for the problem was quantum walks, but then started other research problems. And for example, we can think about the tessellation cover number. Let's say that the cover number is the size of the smallest tessellation. I can have a cover with 1,000 tessellations for this graph here, but that's not necessary to cover the graph. With 3 tessellations, we can cover this graph. And then we are interested in knowing the size of the smallest tessellation cover. And then we have this decision problem, the k-tessellability problem, which is given a graph, decide if the tessellation cover number is less or equal than a constant k. And then we can prove that this problem in general is NP-complete, and of course that for some graph classes it can be easy, and then it's a very interesting problem. Okay, so what we need here is the idea of a tessellation cover. If we have a tessellation cover, then we can define the evolution operators for the staggered quantum walk by following this recipe here. So we need a vector space, which is generated by the vertices of the graph, just the vertices. And then for each clique of this graph, we need to define a unit vector like this alpha here. So it's a linear combination or superposition of the vertices that are in a clique. And then for each tessellation, we have a projector on the space generated by the cliques. Okay? So in the previous example, I would have 3 projectors, 3 unitary operators by following this recipe. In the second example, we have two tessellations, one blue and one red. Then we need two operators. And then the staggered quantum walk will be driven by this succession of projectors. It's similar to the Zegde model that I presented a bit earlier, and they are connected somehow. I will show. Let me give you an example here. So if we follow that recipe for this graph, we have two tessellations, and then we have choose the cliques, we choose a unit vector for each clique. Those coefficients are arbitrary, they can be basically anything, but we can choose them to be like a uniform superposition. We can choose them, they can be all equal. And then if we do reasonable choices like that, we have those matrices, one for each tessellation. We have one operator for the red tessellation, another for the blue tessellation. And let's say that the walker starts here in this black vertex here. Then we apply the red tessellation operator, the operator for the red tessellation. And then it spreads through the vertices of this clique here. Okay? So now it's in a superposition of those four vertices. It does not spread to those vertices that are outside the clique. Now I apply the operator for the blue tessellation, and then it spreads to those other vectors, but not this one, because it's not connected here. It spreads only for those, onto those black vertices. If I apply the red tessellation again, then it will spread to this vertex here. All right? So that's the idea of the staggered quantum walk. And it's interesting because the staggered quantum walk includes all the Zegde model. The staggered quantum walk is more general than the Zegde model. And it also includes the most interesting cases of the coined model. And by most interesting, I mean those cases that are used on algorithms, basically on search algorithms. So if we are defining a quantum algorithm to search for a vertex on a graph using a quantum walk, then we need some kind of pointed quantum walk with a specific shift operator, and then it's all included in this staggered model. We can prove that they are equivalent. So for example, the element stickiness algorithm, which was based on the Zegde model, it can be written as a staggered quantum model. Okay, so those were the most important discrete time quantum walks, and now we also have the continuous time quantum walk. So the idea is that, as I mentioned, the evolution of a quantum system is described by a unitary operator, of course, but more generally, we can describe the evolution by the Schrödinger's equation. We have this differential equation. It's more general than the previous equation that I presented. And if, well, we have here this operator, which is the Hamiltonian. If this Hamiltonian is time independent, then we can solve the differential equation, and then we recover this unitary operator here. But in a more general setup, we can have a time-dependent Hamiltonian, and then it's a bit different. So we need this Schrödinger's equation to define the continuous time quantum walk. And the idea is very simple. The idea is that we can take the Laplacian matrix of a graph, and we can plug that matrix in the Schrödinger's equation, and then it defines a consistent quantum walk. It will describe a quantum walk on that graph. And we can have this coefficient here, this gamma, which defines the transition ratio of the walk. We can like adjust the speed of the transitions. Okay. So those were the most used, the most important quantum walk models, and there are many others. Now I will talk a little bit about how we can implement those quantum walks. Of course, we would need a quantum device to run those quantum walks. As far as I know, we don't have a commercially available device to implement a general quantum walk, nothing like that, but we have available devices to implement more general types of quantum algorithms, like the IBM computers or Getty or IQ and so on. And we can use those devices to implement quantum walks. We can also simulate those quantum walks on classical devices, mostly to study them and to find, make numerical observations about the quantum walks. So let's start by the classical simulation. If you want to classically simulate a quantum walk, we basically must do a matrix vector multiplication. Those matrices are usually very, very sparse, and the state vectors are usually very large in general. And then we have different approaches. We can write our own code from scratch using, for example, NumPy or something like that. We can also use a specific software for quantum walks, like I will talk about HyperWalk. There are some other tools that can be used. And we can also use those frameworks that are developed for general computers like QSE. I will very briefly show some differences between them. I'll just show some snippets of some codes just to have an idea of how they differ. So, for example, we can use a code similar to that to simulate a one-dimensional quantum walk on a cycle, let's say. So I start by importing some libraries and defining some useful functions. That's what I would usually do. And then I would define the initial state, something like that. And so I define the coin state, the position state. I apply the Kronecker product between them. And then I would have some part of the code to actually do the evolution. So I apply the coin and the shifts several times. I repeat the coin operator and the shift operator several times. And that's the idea of a NumPy simulation of a quantum walk. So I needed basically 3 slides here to show the sketch of the code. Of course, I omitted some parts, but that's essentially what I would do. And then we have some specific tools like HyperWalk, for example. And HyperWalk is focused on HPC simulation, but I also find it useful as a learning tool, so that's why I suggest it here for those who are interested in studying more about the subject. And then on a single slide, you can write a code to simulate a quantum search algorithm on a complete graph. So we define the adjacency matrix for a complete graph, and then we define a pointed quantum walk just by this line of code, and then we run that quantum walk for a certain number of steps that we know from theory that is the number of steps that we need to find the market state, and then we can measure the state by this final command here. And then of course I had to omit 1 or 2 lines of code here as well, but to keep it on a single slide, but then you can see that it's much shorter than the previous example. Okay, so the search for a market vertex on a complete graph is basically Grover's algorithm, which you probably have heard. It's a very famous quantum algorithm, and it's equivalent to search on a complete graph. And then we can also use Qiskit, and it's interesting because we can use that to simulate classically a quantum walk, but I can also use that approach to actually implement a quantum walk on a physical device. So if I have access to an IBM quantum computer, for example, or any other quantum computer, let's say Rigetti or something, I can implement quantum walk by doing something like that. So if I have a cycle, let's say, I can define a circuit to move the walker like clockwise or counterclockwise, so we have those simple circuits to increment or decrement a position, and then the overall circuit would be something like that. We have a point operation and then a shift operation represented here. So if the point is set to 1, then I increment the position. If the point is 0, I decrement the position. I walk counterclockwise, for example. So we just have to implement that circuit in Qiskit. So essentially, I would import Qiskit, and then I would probably need to define some auxiliary functions, like I omitted the code because it's not the point here, but we can implement a generalized Toffoli gate like this one, and then I can implement this circuit for walking clockwise, which would be this first part of the circuit. Then I do something analogous to the, well, it's wrong here, to decrement, at the decrement gate, I can implement it as well. And then I set up the circuit, the classical register, and everything. And then I run the quantum walk in this final part here of the code. And it would be essentially the approach to not only simulate classically the quantum walk, but also to run it on a quantum device. Of course, that if we try to do that on one of those devices that we have nowadays, the results will be very poor, very noisy. Wouldn't be able to extract anything very useful, but it's interesting from a theoretical point of view, at least. Okay, so now let me talk about some algorithmic applications. As I mentioned, we can use quantum walks to search for a vertex. That's the most common application of quantum walks. So let's say we have a grid, and we have one vertex of this grid that has some special property, and we want to find that vertex. And let's say that we can only move to the neighbors of each vertex. So classically, I could imagine a situation where I am stepping on the state and can check the property for that state. And the next step, I can only check the properties of one of the neighbors, and then I keep doing that. And if I think about a classical algorithm to find special vertex on the grid using this approach, then classically I would have to visit basically all the vertices of the graph. The complexity of the algorithm would be O of n. I would need n queries on the graph. If I use Grover's algorithm with this constraint, with this restriction, then it would also be O of n. It was proved by Benioff that Grover's algorithm does not happen at all in this kind of special search problem. But if we use quantum walks, then yes, we can have a speed up. So Ambanis, Kent, and Grivosh, they proved that the quantum walk can find the marked vertex in square root of n times a logarithmic factor. And we can even square that logarithmic factor by doing some tricks. For example, Tulsi proved that we can do that by adding an auxiliary qubit and then doing some controlled operations. But there are some other tricks also that we can apply that works as well. And the idea here is very similar to the previous quantum walk that I mentioned. We just have to do a small modification in the coin, the small perturbation in the coin. Basically, the coin must behave in two different ways. One way if it's stepping on the market coin, a market state, and in a different way if it's not. Okay. So it's an example using the coined model. Another example of an interesting algorithm using the Zagdi model is the element distinctness. So basically, we want to check if there are repeated elements on a list. Then, classically, we would need O of n queries to that list, but quantumly, we need n to the power of 2/3. So there is a speed up. And it's based on a quantum walk on a Johnson graph. Johnson graphs, like this one. So it's a bipartite graph, and we can apply the Zagdi model. So I mentioned an example with the coined model, one example with the Zagdi model, and now one example with the continuous time quantum walk. We can use the continuous time quantum walk to find the exit to the, of course, it's a very artificial problem. I don't know any application for this problem, but it's interesting from a theoretical point of view. We can assume that we start on this vertex here. It's the root of a binary tree. So we have a binary tree here, and we have another binary here, a binary tree here. And then we connect the leaves randomly. And then we want to go from one root to another root. And if you try to do that classically, the heating time is exponential on the number of nodes of those trees. And quantumly, it's polynomial, so it has an exponential speed up. And the intuition behind that is that you can see that the classical quantum walk will get stuck here in the middle. So it will keep going back and forth until it eventually escapes that middle and then finds the exit. But the quantum walk, it goes like a wave. It doesn't stop at all here. So it finds the exit much faster. So it's interesting because it's an example with exponential speed up. Even though it's very artificial, it's not a real world problem, but it's interesting anyway. We also have this example that works both on the continuous time and in the discrete time. It was originally developed in the continuous time setup, but then it was rewritten in the discrete time as well. It's an algorithm to evaluate an AND formula. So we have a Boolean expression made by NAND operations, and then you can represent that expression by a binary tree. and then we basically walk on that tree, and we measure after a certain number of steps or after some evolution time, and then depending on where we find the walker, we can say the outcome of the expression is true or false with a high probability of success. And it has also an interesting speed up compared to the best classical algorithm. We also have a family of algorithms, or let's say a framework to develop quantum algorithms, which is the QA-OA. So just a little bit of history. The QA-OA is a framework to develop quantum algorithms for optimization, and it's been applied a lot on real devices because it allows you to make more compact circuits. So one problem with current devices is that it cannot run very large circuits because the noise accumulates, and then at the end you don't get any useful result. So one solution to keep the circuits very shallow, very short, is to use this approach, this QA-OA approach, which is based on an alternation of very simple operators and of very simple sub-circuits, let's say. And those sub-circuits, they are parameterized, so we run the quantum circuit and then we send the outcome to a classical computer, and this classical computer, with a classical optimization algorithm, it helps to choose the next round of parameters for the circuit. So it's it keeps iterating until the parameters converge to good ones. It's very similar to artificial neural network. So in a neural network you have weights and you have to optimize those weights. And here it's basically the same thing. You have to optimize some parameters on the circuit. So that's a very general approach, and the QAOA is a subcase. It's a modification of QAOA where one of those operators, remember that I mentioned that we alternate two operators, right? One of those operators are replaced by a continuous time quantum node. That's the idea. So it's a classical quantum algorithm. It works together with a classical computer. So that's the idea of the circuit. We have here on the left a circuit. Notice that we have those gamma parameters that we have to optimize. And then on the right we have another operator that we can interpret as a continuous time quantum walk. And then notice that we have T, time, the evolution time of the quantum walk. And this evolution time is the parameter that has to be optimized. So if we find the optimal running time for the quantum walk, and we find that with help of a classical computer, then we can find good solutions for optimization problems. And it's a way of finding short circuits that work with a classical computer to find good solutions for optimization problems. And the circuits can be very efficient if we follow some assumptions, if there are some requisites to find good circuits. They are on that paper. I can share, of course, those slides for those who want to see that in more details. But let me move on because I'm ahead of time here. Then, as a final note, I can say that quantum walks can be used to implement basically any quantum algorithm, because there is this very interesting result by Andrew Childs that proves that quantum walks are a universal model for quantum computation. So at least in principle, you can do anything that you can do with a quantum computer. You can do it with a quantum walk. You could build a quantum computer based on a quantum walking principle. Of course, that the details about how to do that physically are way beyond my comprehension, because I'm not a physicist, I'm a computer scientist, so I don't know how complex that is, but at least in a theoretical point of view, it is possible. So that's something that I find very interesting in quantum walks. So that's it. Thank you once again for the invitation. And if you have any questions.
The QAOA exam at the end.
Sorry?
The QAOA exams at the end. Do I understand correctly? You just have a single parameter you're optimizing, which is the time for the mixable?
Yes, you have, for this part of the circuit here, you have the time, yes. Here, in this part of the circuit, the parameter to be optimized is the time.
And is this going to be the same time in each leg or a different time in each leg?
Yeah, it's one time for this part of the circuit, yes. For this part of the circuit it would be one time, but then you will run it with different run times, because you iterate that on a classical computer.
But you only have, that's the full circuit, you're not applying
Yeah.
it to
That's the quantum part of the circuit, yes.
That's the full quantum.
The full quantum circuit, yes.
But it's a single layer QAOA.
Size from
I see. No, you can have, no, I see your point now. Yeah, no, you can have more layers. You can have
Then
more
you'll
layers.
have a different time.
Yeah,
the same
that's
time
it,
each day, or
yeah.
different
Yeah, same time for each layer, yes. But then you can have more layers. Yes, just like.
So it's a single parameter optimization.
Yeah, you have the same parameter for each layer, but then you can repeat that.
Are there convergence guarantees or anything, or is this purely heuristic?
It's a risk, yeah, we don't have guarantees.
So why do people like it over a standard QAOA? Because I mean, that looks quite painful to me.
Yeah. It has been applied to some problems like portfolio optimization, vehicle routing, and it has been shown that for some problems you can have a better convergence, because the quantum walk, the intuition behind that is that the quantum walk can take advantage of the structure of the problem much more than the general QAOA. Another question?
I didn't understand when you showed the example of the search of a site in the lab. I didn't understand why Robert's algorithm
Yeah, here.
and complexity.
You mean in the complete graph or in?
Well, my understanding is that if you write the right oracle, Grover's algorithm should always be order of square root of n. So when you said it's order of n, I was lost. So this must be with some assumption on the oracle.
Yeah, the assumption here. Let me see if I can find here, right? This slide, right?
Exactly.
Yeah. That's because the assumption here is that we cannot write an oracle that has access to every vertex.
Okay.
If we have access to any vertex in instant time, then we have a complete graph.
Okay.
And then it's equivalent to Grover. But in this problem, we must have a restriction that I can if I check this vertex, let's say, in one step, then on the next step I can only check the neighbors. So it's much slower than Grover. Yes?
So I also have a question on this. So obviously Grover is basically the core idea of amplitude amplification, which is then fundamental primitive and
Yeah.
hard quantum algorithms and is super useful.
Yeah.
Is this also a useful primitive in other quantum algorithms? Like can it, so amplitude amplification is used with quantum signal processing, block
Yeah.
encoding, double state prep, all sorts of funky things.
Yeah.
Do you ever, the interesting problems have this kind of constraint where you can only look at one vertex each, and so the quantum round walk is the way forward and speed up that algorithm?
You mean if quantum walk is can also be seen as a general framework, like
Yeah, or like particularly this one, like this particular search.
Yeah.
Like I can kind of imagine that you could have algorithms where somehow you can only look at two states at a time and you need to figure out which is better, but I'm not seeing examples like that. So could this be used as a primitive that speeds up, I don't know, double state prep or some kind of quantum signal processing algorithm or non-linear sequence equations?
Yeah, it's very general for search on graphs. So if you have a problem that can be written as search on graph, then this approach is very general.
Give me an example of one. So I kind of imagine it also, but I can't see them right now.
Yeah. Well, element sequence is a good example, I think, because we have a problem of deciding whether a list has some repeated element, but then we can rewrite that problem as a search for a vertex on a Johnson graph. So we can prepare a graph like this one. Oops. Yeah. Where each vertex of the graph is a subset of the list. We have subsets with 2 or 3 elements in this example. And then we connect the nodes if they differ by only one element. That makes this Johnson graph. And then the problem of deciding if the list has repeated elements can be written as searching for a vertex in the graph. So it's a search problem. And so in this sense, yes, it's very general. Yeah, I don't know if that's what I have in mind.
Maybe we can chat more.
Okay, yeah, sure, yeah. Yes?
Doesn't already building this graph need more than ON operations?
That's a good question, yes, because these complexities are basically query complexities, so you're abstracting now the trouble to build the circuit. So yes, when we build the full circuit, the complexity will be higher than that, but it will still be better than classical. Even though it's more difficult to justify, but I had this question in the past, and yes, that's good. Because as you can see, I don't know, I think like that. It's a bit scary because when we want to implement, in this example, or I gave some other example here as well, when we want to implement a quantum wall on an explicit circuit, it's kind of painful because there are several gates, but for some cases we can still do it efficiently. Even though it looks ugly, but it's still efficient.
I think I was specifically referring to mapping the search to the graph.
Okay.
Because the graph has more nodes than the list has entries. So
Okay. Yeah.
building the graph is more costly than searching the full list.
Okay. Yes.
But I get this was like an example, right?
Yes, the graph is much larger than the list, but then what you have to keep in mind is that you don't have to, you don't need all those quantum states, because here you basically need enough quantum states to represent a very small subset of the list. Here I have only 2 elements of the list, and here I have only 3 elements of the list. So the quantum states are much smaller because it's a logarithm of the size of the graph. So it's much more efficient because of that. You don't need to, even though the graphs seems very large, you don't need all those quantum states.
Okay, let's thank Franklin again.